When installing light standards in parking lots, ensuring proper grounding and bonding is crucial for electrical safety. The use of a number 4 bare copper wire clamped to the reinforcing bars of the concrete cylinder as a grounding electrode is a common practice. The electrical contractor connected this wire to the factory lug inside the handhold of the post and ran 2 number 10 American wire gauge wires from the panel to the light fixture for the 240-volt system. The key concern here is whether this configuration provides adequate grounding and bonding as per the National Electrical Code requirements. Article 410.21, which pertains to luminaires, lamp holders, and lamps, states that electrical equipment shall be grounded by one or more grounding conductors that are connected to both the equipment and the grounding electrode system. The number 4 bare copper wire, in this case, is considered an equipment grounding conductor, or EG, as defined in Article 100. The equipment grounding conductor is the conductive path that provides the grounding of equipment. However, simply having an equipment grounding conductor may not be sufficient. Article 250.60 requires bonding between exposed non-current carrying metal parts, such as the light standard, and the grounding electrode system, which includes the power source. Electrical systems and circuits shall be bonded and grounded in accordance with this article. The critical point is that the lone number 4 bare copper wire, while serving as an EGC, might not provide adequate bonding back to the power source. To ensure proper grounding and bonding, several measures should be taken. Firstly, a minimum number 6 American wire gauge copper EGC should be installed for the 240-volt circuit, as per Table 250.122 in the National Electrical Code. Table 250.122 provides minimum equipment grounding conductor sizes for grounding raceway and equipment. Secondly, an additional bonding jumper should be installed from the EGC to the power source, such as the panel ground bar. This bonding jumper ensures a low impedance path for fault current to flow back to the source, facilitating the operation of overcurrent protection devices. In conclusion, while the number 4 bare copper wire satisfies the requirements for an EGC, an additional bonding jumper is necessary to complete the grounding and bonding circuit and ensure electrical safety. This configuration provides a reliable path for fault current, protecting both equipment and personnel. To elaborate further on the function and necessity of each component, let's examine the equipment grounding conductor, the bonding jumper, and the grounding electrode system in more detail. The equipment grounding conductor, as previously mentioned, provides a low impedance path for fault current to return to the source. In the event of a ground fault, such as a short circuit between a live conductor and the metal enclosure of the light standard, the EGC allows a large amount of current to flow back to the source. This high current triggers the overcurrent protection device, such as a circuit breaker or fuse, to trip and disconnect the circuit, preventing electric shock and equipment damage. The size of the EGC is critical, as it must be capable of carrying the fault current without overheating or causing excessive voltage drop. Table 250.122 in the National Electrical Code provides the minimum size requirements for EGC based on the rating of the overcurrent protection device protecting the circuit. In this case, with a 240-volt circuit protected by a specific amp breaker, a minimum number 6 American wire gauge copper EGC would be required. The bonding jumper, on the other hand, provides a connection between the EGC and the grounding electrode system, ensuring that all metal parts of the electrical system are at the same potential. This is particularly important in reducing the risk of electric shock, as it eliminates voltage differences between different metal parts. The bonding jumper also helps to reduce electrical noise and interference, improving the performance of sensitive electronic equipment. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, metal water pipes, or concrete encased electrodes. These electrodes are connected to the earth, providing a low resistance path for fault current to dissipate into the ground. The grounding electrode system is intended to stabilize the voltage to earth during normal operation and to provide a path for fault current in the event of a ground fault. The National Electrical Code specifies the requirements for grounding electrode systems in Article 250, including the types of electrodes that are permitted, the minimum size and installation requirements for grounding conductors, and the methods for bonding different grounding electrodes together. In the case of the light standards in the parking lot, the reinforcing bars of the concrete cylinder serve as a concrete encased electrode. This is a common and effective method for grounding, as the concrete provides a large surface area for contact with the earth, reducing the resistance to ground. However, it is essential to ensure that the reinforcing bars are properly connected to the grounding system and that the connections are protected from corrosion. Now, let's consider the specific scenario described earlier. The electrical contractor installed a number 4 bare copper wire connected to the reinforcing bars and then to the factory lug inside the handhold of the post. While this arrangement provides a connection to the grounding electrode system, it may not be sufficient to ensure proper bonding back to the power source. The problem is that the number 4 bare copper wire only connects the light standard to the ground. It does not provide a direct connection between the light standard and the neutral conductor or the grounding busbar at the power source. As a result, in the event of a ground fault, the fault current may have to travel a long distance through the earth to return to the source, increasing the impedance of the fault current path and potentially delaying the operation of the overcurrent protection device. To address this issue, the electrical contractor should have installed an additional bonding jumper from the equipment grounding conductor to the power source. This bonding jumper provides a lower impedance path for fault current to flow directly back to the source, ensuring rapid operation of the overcurrent protection device. The bonding jumper should be sized appropriately for the circuit, as specified in Table 250.122. In addition to the bonding jumper, the electrical contractor should also have ensured that the equipment grounding conductor was properly sized for the circuit. As mentioned earlier, a minimum number 6 American wire gauge copper EGC is required for a 240 volt circuit protected by a specific amp breaker. If the equipment grounding conductor is too small, it may not be able to carry the fault current without overheating or causing excessive voltage drop, which could delay the operation of the overcurrent protection device. In summary, to properly ground and bond the light standards in the parking lot, the electrical contractor should have installed firstly a minimum number 6 American wire gauge copper EGC for the 240 volt circuit as per Table 250.122, and secondly, an additional bonding jumper from the EGC to the power source, such as the panel ground bar. These measures ensure a low impedance path for fault current, protecting both equipment and personnel. Furthermore, it is important to note that the National Electrical Code is updated regularly, and it is the responsibility of electrical contractors and inspectors to stay current with the latest requirements. The 2002 edition of the National Electrical Code was referenced. It is important to consult the most recent edition of the code to ensure compliance with current standards. In addition to the technical requirements for grounding and bonding, it is also important to consider the practical aspects of installation. The connections between grounding conductors, bonding jumpers, and grounding electrodes must be made properly and securely, using approved connectors and methods. The connections must also be protected from corrosion, as corrosion can increase the resistance of the connections and reduce their effectiveness. Finally, it is important to document the grounding and bonding system, including the size and type of conductors, the location of grounding electrodes, and the methods used for making connections. This documentation can be helpful for future maintenance and troubleshooting. Grounding and bonding are critical aspects of electrical safety, and it is essential to follow the requirements of the National Electrical Code to ensure the safety of people and property. Now let's delve into the specifics of selecting the correct size for the equipment grounding conductor, often abbreviated as EGC. As previously mentioned, Table 250.122 in the National Electrical Code provides guidance on the minimum size of EGC based on the rating of the overcurrent protective device in the circuit. For example, if the 240 volt circuit for the light standards is protected by a 20 amp circuit breaker, Table 250.122 would likely specify a minimum number 12 American wire gauge copper conductor for the EGC. However, if the circuit is protected by a 30 amp breaker, the table may require a number 10 American wire gauge copper conductor. It's crucial to consult the specific table and match the conductor size to the overcurrent protection rating to ensure adequate fault current carrying capacity. Beyond simply meeting the minimum size requirements, there are situations where increasing the size of the EGC may be beneficial. For instance, if the circuit run is particularly long, increasing the EGC size can help reduce voltage drop and improve the performance of the grounding system. Additionally, in environments where there is a high risk of corrosion, using a larger EGC can provide additional protection against degradation and ensure long-term reliability. Another important aspect of selecting the appropriate EGC is considering the type of conductor material. While copper is the most common material used for EGC, aluminum conductors are also permitted under certain conditions. However, when using aluminum conductors, it's important to ensure that they are properly sized and terminated to prevent corrosion and ensure reliable connection. The National Electrical Code provides specific requirements for the use of aluminum conductors in grounding systems, including the use of approved connectors and antioxidant compounds. Furthermore, the path of the EGC is also an important consideration. The EGC should be run along with the circuit conductors, either inside the same raceway or cable assembly. This helps to minimize the impedance of the grounding path and ensure that the fault current can flow quickly and efficiently back to the source. Avoid running the EGC separately from the circuit conductors, as this can increase the impedance of the grounding path and reduce the effectiveness of the grounding system. Now let's discuss the importance of proper bonding techniques. Bonding is the process of connecting all metal parts of an electrical system together to create a common electrical potential. This helps to minimize voltage differences between different metal parts and reduce the risk of electric shock. The National Electrical Code requires bonding of all non-current carrying metal parts of an electrical system, including enclosures, raceways, and equipment frames. Bonding can be achieved using various methods, including bonding jumpers, bonding bushings, and grounding clamps. Bonding jumpers are typically used to connect metal parts that are not directly connected to each other, while bonding bushings are used to connect metal raceways to enclosures. Grounding clamps are used to connect grounding conductors to grounding electrodes. It's important to ensure that all bonding connections are made properly and securely, using approved connectors and methods. The connections should also be protected from corrosion to ensure long-term reliability. In addition to bonding the non-current carrying metal parts of an electrical system, it's also important to bond the service equipment to the grounding electrode system. This is typically achieved by connecting a grounding electrode conductor from the service equipment to the grounding electrode. The grounding electrode conductor should be sized appropriately for the service entrance conductors, as specified in the National Electrical Code. The grounding electrode system should consist of one or more grounding electrodes, such as ground rods, metal water pipes, or concrete encased electrodes. The grounding electrodes should be installed in accordance with the National Electrical Code and should provide a low resistance path to ground. In summary, proper grounding and bonding are essential for electrical safety. By following the requirements of the National Electrical Code and using approved materials and methods, electrical contractors can ensure that electrical systems are safe and reliable. Let's expand on the grounding electrode system itself. As noted, the National Electrical Code permits various types of grounding electrodes, each with its own installation requirements and considerations. Ground rods are a common choice, typically consisting of copper-clad steel rods driven into the earth. The code specifies minimum length and diameter requirements for ground rods, as well as the spacing between multiple rods when more than one is used. The resistance to ground of the ground rod system should be measured and should not exceed 25 ohms. If the resistance exceeds 25 ohms, an additional ground rod or other grounding electrode may be required. Metal water pipes can also be used as grounding electrodes, provided that certain conditions are met. The water pipe must be in direct contact with the earth for at least 10 feet and must be electrically continuous. The water pipe must also be supplemented by an additional grounding electrode, such as a ground rod or concrete encased electrode. Concrete encased electrodes, also known as U for grounds, consist of a length of bare copper conductor encased in concrete. These electrodes are typically installed in the footing or foundation of a building and provide a very effective grounding path. The concrete provides a large surface area for contact with the earth, resulting in a low resistance to ground. The National Electrical Code also permits the use of other types of grounding electrodes, such as ground plates and chemically enhanced electrodes. However, these electrodes must be installed in accordance with the manufacturer's instructions and must meet the requirements of the code. Regardless of the type of grounding electrode used, it's important to ensure that the grounding electrode system is properly installed and maintained. The connections between the grounding electrode conductor and the grounding electrodes must be made properly and securely, using approved connectors and methods. The connections should also be protected from corrosion to ensure long-term reliability. Furthermore, the grounding electrode system should be inspected periodically to ensure that it is still functioning properly. The resistance to ground of the grounding electrode system should be measured and should be compared to previous measurements. If the resistance has increased significantly, it may indicate a problem with the grounding electrode system that needs to be addressed. Now, let's address some common misconceptions about grounding and bonding. One common misconception is that grounding is only necessary for safety. While safety is certainly a primary concern, grounding also plays an important role in the proper functioning of electrical equipment. Grounding helps to stabilize the voltage to earth and reduce electrical noise and interference, which can improve the performance of sensitive electronic equipment. Another common misconception is that bonding is only necessary for metal parts. In fact, bonding is also required for other conductive materials, such as plastic pipes and composite materials. The purpose of bonding is to create a common electrical potential between all conductive parts of an electrical system, regardless of the material. Another misconception is that a single grounding electrode is sufficient for all situations. In some cases, a single grounding electrode may be adequate. However, in other cases, multiple grounding electrodes may be required to achieve a low resistance to ground. The number of grounding electrodes required depends on the soil conditions, the size of the electrical system, and the requirements of the National Electrical Code. A further misconception is that the grounding conductor is only necessary in the event of a fault. In reality, the grounding conductor plays an important role in the normal operation of an electrical system. The grounding conductor provides a return path for fault current and helps to ensure that overcurrent protection devices operate properly. Another misunderstanding is thinking that all green wires are grounds and are safe to touch. Green wires are generally used for grounding conductors, but they can become energized under fault conditions. It's always important to treat all wires with caution and to use appropriate safety precautions when working with electrical systems. Finally, always remember to consult the latest edition of the National Electrical Code and to follow the manufacturer's instructions when installing and maintaining electrical systems. Grounding and bonding are complex topics, and it's important to stay current with the latest requirements and best practices.